Hi, my name is Patrick Kling, and I'm an engineering manager on the Healthcare and Life Sciences team here at Google Cloud. Our mission is to organize the world's healthcare information and to make it accessible, secure, and useful to improve the health and healthcare of people and communities globally. Today, we're going to talk about our offering in the medical imaging space. First, we'll hear from Omer Khawar, who is the VP of Engineering at iDigital. His company built an innovative teleradiology solution on top of Google Cloud Platform. Afterwards, we'll hear from my colleague, Sasha Sicular, who'll be walking us through the cloud architecture of this system. And then finally, I'll be back up here, and I'll be talking about the platform underpinning all of this, which is the Cloud Healthcare API. And with that, I'll hand it over to Omer.
Thanks, Patrick. Hi, everybody. Thanks for coming. I know it's the last day, and people probably have flights and things that they want to get back to, so I appreciate the people that did come. We have a lot of exciting things to talk about today. At iDigital, our mission is to essentially deliver better patient outcomes through the application of advanced technology. When our founders sat down, they looked at the entire healthcare sector and determined that the area of the industry that was most ripe for this kind of benefit was, in fact, radiology, and specifically teleradiology. So they thought about the problems that they were trying to solve. There are over 35,000 radiologists. Less than 3% of them are networked. There's no common platform and a decided lack of technological advancement. This market is very large. It's $5 billion. But it's a highly fragmented mix of solutions. And so what we're running into is essentially two major areas of challenge. In the market itself, we've got radiologist burnout happening. Now, there's a couple of factors that are feeding into this. One is that radiologists are being asked to read more and more, so the volumes are increasing. Also, radiologists are being asked to do it faster. Oftentimes, there are patient expectations. I'd like my reading back fast. There are also clinical concerns. If there are emergent indications that things need to be turned around rapidly. So whilst the volume's going up and people are asked to do their work faster, the technology hasn't been able to keep up. In addition, another trend that's worrying is that coming out of medical programs, we're having fewer and fewer people actually opt to do radiology. So all these factors are driving radiologists individually to try to do a lot more on the same platforms and systems that they've been using for decades. We looked at some market surveys and found that satisfaction amongst the users and users of the radiologists is down at the 40% level. And for a 5 billion market to be down that low, and just to be clear, that 40% satisfaction is with any of the solutions that exist. It wasn't their particular solution. So they're essentially saying there's nothing there that really helps me execute my work rapidly and achieve those patient outcomes that we're looking for. And finally, with the trend in fewer and fewer radiologists and the increasing cost of healthcare that everybody's aware of, we're finding that we get very poor rural coverage. And institutionally also, there are challenges in delivering radiological care. On the technology side, we've got a lot of problems. We've got cumbersome data exchange. So with any technology that has been around for a few decades, what we're finding is we've got a lot of different systems. They all speak a little bit differently, and so we've got all of these point-to-point integrations going on. And that's in the radiology workflow. So from end to end, they could touch 4 or 5 different systems provided by 4 or 5 different vendors. And as those vendors have software that gets released, we essentially have problems in those integrations. That's leading to low reliability. So it is not uncommon, and people that are not in the field may be shocked by this, but it's not uncommon for radiologists to essentially show up to work and not be able to work. their platform that allows them to do teleradiology just is not available for hours at a time. And finally, low innovation. So I mentioned that before. With the legacy systems that are in place and the technology that exists, what we're finding is it's very hard to get some of the cutting edge technologies, specifically machine learning models and artificial intelligence, to be applied. People are working very hard, some of you are in the room, on these technologies, and they're running into real challenges in delivering that into the workflow for radiology. I was talking to one vendor that has to actually, they're a team of data scientists and they have to take VMs and put them in sites in order to deliver that. This is really, these high roadblocks are causing people just not to use the technology. And then finally, scalability. So all of the things I talked about from a fragmentation perspective, from a technology perspective, are leading to an inability to scale any of the individual solutions that are on the market today across the country. So our solution. So what we looked at was to create a cloud-native, zero-footprint teleradiology solution. The entire solution is built on the cloud, including the DICOM store. So for those of you not in the industry, that's essentially the images from the various modalities. So those are on the cloud, which is, believe it or not, a significant step. There's an embedded DICOM viewer, so that also is in the cloud. And so that's important to reduce the multiple vendor approach that currently exists today. And then both RIS and PACS capabilities are built into the platform. From a machine learning and AI support perspective, step one was to create a platform and then start to drive in the capability to add machine learning and AI from cloud solutions that exist today. Embedded voice support is an important work enabler for radiologists, and then streamlined integration with facilities. So those of you that don't work in the space may not understand how difficult it is to actually connect to facilities, whether that's a hospital or an urgent care center in some rural area. But after we went live as VP of engineering, those were all my problems. And so it was great to get some of the experience on our team, decades of experience doing this at the beginning so that we could build into our solution capabilities that actually make that faster. It seems like the simplest thing to do, but it's actually been the hardest to achieve in practice. So now I'll talk about the platform itself. So those capabilities can be broken down into technical building blocks. Later on, we'll go through this in detail, so I'm not going to spend too much time on this slide going through every bullet, but I do think it's important to kind of have some context for the capabilities that are there. Data ingest. So as I said, many points. This is all HIPAA data, so it contains patient information. The images themselves need to be secure. So we needed to make sure it was both secure and scalable to thousands of points. And so you'll see that in our solution today, later on. The platform itself. So this essentially is the work management. It's the workhorse of the platform. And that's doing all of the management of the work that's coming in, assigning that out to radiologists, managing access, all of those things that you would expect from a work manager. This is also where we would introduce clinical AI-based decision-making. The image viewer. It's already on the cloud. Our images are on the cloud. We have very low latency in image fetch, which, again, is a challenge based on what I've described today. And messaging. So again, we'll talk about this in detail, why we went this route, but it was important to have the scalability within the system to pass information back and forth. And mobile. So I think I referred to earlier kind of a lack of access from an institutional perspective. So we made a mobile tool set that allows essentially mobile radiology to be enabled. Essentially, these are technicians that drive around with a mobile unit, and they can visit institutions such as jails or hospitals, elder care centers, and our platform enables that workflow also seamlessly. And finally, machine learning. So, that's really I think the point of making a new platform is to enable that. And we'll talk in detail about how we did that and what the capabilities are to essentially create that continuous loop of learning. And then underneath this all, a data store. So it was important that the data be very close to the application. The latency that users experience today is very much related to where the data is. Where are the images? Where's the patient data? And so it's very important to bring that close and on the same platform. So why did we pick Google for this solution? Well, as you can see on the left side, all cloud services provide a set of capabilities. And so what distinguished Google for us was really that they had created and were in alpha with a HIPAA-compliant data store. And that was the crux of the decision. Also, the seamless scalability that we get with Kubernetes, multi-region networking, and then the rapid ML tools that some of you have seen today, and additions to those that were announced at the conference. So what does that mean from an engineering perspective? Well, it meant that I could work with our design teams, our SMEs in the space, and essentially use these tool sets and accelerate the delivery of the platform itself. I don't need to sit there and redesign everything from scratch. My engineers don't need to go in and make all of these things. I can leverage the services and capabilities that Google has. And later on, we'll talk about specifically which ones. So what did we learn working with Google? Well, we found them to be a very active partner. As we went and designed our solution, there was very much a conversation with them about the approach we would take, how we would solve various problems we ran into. And I can't speak enough about the healthcare team. They were awesome throughout the process. In addition, we worked with Zasmic, our engineering partner, and they were critical too in getting to market fast. So again, some of the cloud services I mentioned that accelerated our time to market. And we'll go through those in detail. So technical lessons learned. Going through this process of making this platform from scratch, cloud native, there were a couple things we learned that are pertinent in healthcare. So number one, resource matching was a key activity. So what do I mean by that? Essentially, as we found these pieces of data coming from various sources, getting that data associated with both the patient and the order that was going on was critical. And to be able to do that at scale. So we're talking petabytes of information that needs to hook together and be related at the point that the radiology is trying to perform their tasks. Association of DICOM-based studies with orders has many edge cases. So those of you that have tried to use this standard will understand the standard is not standard. And every vendor has interpreted it their way. And then finally, scaling. We needed to scale fast, and we needed to scale without affecting our production clients. So we solved this in the first case with microservices and PubSub, and in the second case by introducing and accommodating the flexibility that exists in DICOM, and on the third with GKE. And we're looking at Istio and Service Mesh. There was an announcement at the conference on Service Mesh also that we're very interested in. So we'll continue to work with Google and with our engineering partners to achieve those. So next, Sasha is going to come up and talk about the architecture in detail.
Thank you, Omer. Appreciate everybody being here. I'm very grateful to be on this stage and talking to you all about this very interesting solution. A little bit about myself. Before joining Google, I was director of medical informatics at Columbia University for many, many, many years, many more years than I'd like to admit. And it's from that background and learning that I have an appreciation for many of these technical challenges that organizations are trying to solve, large and small, ultimately to drive better patient outcomes. So what we're going to do today is talk through the specific architecture that we put in place for with iDigital to help facilitate this zero on-prem footprint, entirely cloud-based solution. I'll just highlight a couple of the steps right now. Some of the key things that I think everybody should be focused on: networking. So networking is critically important, of course. As soon as you start talking about moving to the cloud, how are you going to facilitate that? So the network connectivity is absolutely critical. From that, we move deeper into the stack. We talk about how Google Cloud Platform organizes its internal structures around the concept of a project. MLLP and DICOM, those are two critical legacy protocols that are ubiquitous in the healthcare space. And any organization looking to move into this kind of method of working in the cloud needs to understand the limitations of both MLLP and DICOM and how you can overcome those limitations. And we'll talk about that in a little bit more detail. From there, I want to point out, obviously, the healthcare API. The healthcare API is really pivotal and central to the entire conversation of the architecture, what it allows you to do, the kind of capabilities it provides, the kind of systems and services you can build around it. And then ultimately, the healthcare API will go into even further detail with Patrick when he speaks in the third act. Omer picked up on something very quickly, which was, I like to think of it as liberating data. So right now, to facilitate day-to-day transactional operations between providers and patients, those data systems are siloed. They're isolated within the on-prem environment. As we move into the future, the question becomes, how do we leverage that data to provide better service? Again, ultimately driving better patient outcomes, servicing more patients, and really meeting the challenges that all organizations are facing today in healthcare. So by bringing the data to the cloud, you get to take advantage of all kinds of functionality that's present in the cloud. In particular, we'll talk about BigQuery. Underpinning the whole exercise, of course, is security. How do you ensure that you are in compliance with very stringent HIPAA regulation regime? So obviously, HIPAA is the law of the land in the United States. Of course, we have global presence. So we'll talk about HIPAA today, but this same conversation plays internationally. All kinds of jurisdictions are introducing data protection-related regulation in general and also in healthcare. So as an organization that's looking to take advantage of these products and functionalities, you obviously need to make sure that you're doing it in a very secure and regulated fashion. So let's talk about the network connectivity. What are we trying to do here ultimately? We're looking to bring data from where it's being generated into the cloud. And in order to do that, you have to have good network connectivity. If you think about teleradiology, the way that those providers access this information is that they have to get that information from where it's stored. And traditionally, that information is stored on premises, where it's been generated. So think about all of the network connectivity issues that a specific physical facility may have. Now let's turn it around and think about what the networking opportunities and capabilities are of Google. So we have a major networking presence globally with tremendous options up and down the stack, specifically dedicated to networking. Particularly in this solution, we're looking at our Cloud VPN solution. And this is what really enables you to do a fully zero footprint installation. Ultimately, the key thing that the physical facility needs to enable is the VPN termination. If they can enable that VPN termination in their networking stack, connected to its endpoint in the cloud, that's basically all you have to do. Yes, there are other solutions. You can look at various interconnect solutions for higher degrees of bandwidth. You can look at even point-to-point secure tunnel. Those are a little bit higher up the stack. You go from 0 footprint to maybe 99% no footprint. So Cloud VPN was really our first intent and our first interest to facilitate this technology. The key consideration here is that the VPN will route the traffic to the appropriate IP address, not just externally, but also internally. As we continue the conversation, we look at Kubernetes, et cetera, we'll see how all those IP considerations come into play. Project. So I spent a little bit of time earlier talking about this. In Google Cloud Platform, one of the major areas of abstraction in the system is what we call the project. And if for any of you who've worked with Google Cloud Platform previously, you'll be familiar with this concept. The project is where you put all the things. So all of your networking resources, all of your virtual machines, your Kubernetes clusters, et cetera, et cetera. They all exist inside of projects. And why should we consider projects as a major boundary for the architecture of the application? Data isolation. Obviously, as a technical provider, technical services provider, iDigital is looking to onboard many, many customers. We want to ensure that their data is completely isolated from any of the other customers in the system, specifically the hard data, the DICOM images themselves. Also, the project is where billing happens. So when you create a project, you create an associated billing account, and all of the resources and consumption of those resources within that project are then charged into that billing account. So for an organization that's looking to onboard many, many customers, you want to have a very, very close accounting of what those underlying resources are costing. So this, by isolating at the project level, you're able to have a very, very fine-grained control or insight into what all of the resources are costing on a customer-by-customer basis. Again, due to the fact that the project is the kind of base level of abstraction, all of the things that are in the project, healthcare API, Google Cloud buckets, Google Cloud storage buckets, virtual machines, allocation of reserved external IP addresses, et cetera, all of those items have quotas associated with them. So quota management is handled on a project-by-project basis. So again, this is how you are able to isolate various customers from clobbering other customers, et cetera, and they maintain their entire individual ecosystem. And then finally, security. Projects, again, not just data isolation, but access to projects are controlled via IAM, GCP IAM, which is Identity and Access Management, and you can have very, very fine-grained control over which systems, which people, which accounts, which services can access all of the things within the project. So for this particular implementation use case with iDigital, we have many projects at play here. We have production, development, demo, where iDigital is able to spin up a completely de-identified system and demo it to prospective customers, et cetera. What you'll see is, and we'll talk about it in particular, logging. Again, cloud audit logging, stack driver. These are all very important pieces of the overall conversation. And what we in Healthcare and Life Sciences group within Google Cloud recommend as a HIPAA best practice. all of the projects, all of the independent projects in the system can outbound their logs to a audit and logging dedicated project that can be staffed specifically by compliance, a compliance organization, separate group of people, no bleed, anything like that. A project per customer, talked about that a little bit. And finally, all of these pieces can be automated. And this is one of the pieces of the word scale. How do you scale this solution to accommodate, hopefully you're going to do good business. You want to accommodate lots and lots of customers. How do you, as an organization, enable the onboarding of all of these customers and managing of all of these scenarios? It has to be automated. So everything we're going to talk about today can be automated through Cloud Deployment Manager, G-Cloud, Kube Control. Kubernetes. Kubernetes is kind of the base layer of scalable abstraction from a computational perspective. And this particular use case calls for using Kubernetes to scale both the MLP and DICOM adapters and the application-specific services. The key part here is the networking. So the Kubernetes cluster itself controls the ingress networking from your external on-prem customers to their specific MLP and DICOM adapters. Of course, everything in the Kubernetes cluster is connected to the entire logging infrastructure. And what Kubernetes really brings to the table is, as I said, the ability to scale the computation. But on which dimension do you scale? How do you determine when you should scale? There's new developments, of course, always coming new developments. So GKE enables you to scale on custom metrics. So for example, MLP is lightweight from a data perspective. It's high message volume. DICOM is a little bit heavier because it's the actual image. So they have different scaling dimensions. And by integrating with custom metrics for scaling, they can scale independently. MLP and DICOM adapters. This is really a lot of the meat of the architecture. Google publishes open source, MLP, and DICOM adapters. And the way that you should think about them is as a bridge. On one side, they receive legacy MLP and DICOM protocol communication. On the other side, they egress healthcare API protocol. So this is the real workhorse here. This is what enables you to bridge the legacy on-prem environment, the ubiquitous presence of these protocols in virtually all hospital-oriented systems around the world to your cloud-based solution. And again, as I mentioned, these services are exposed via private internal load balancer IP addresses. Those addresses, in turn, are routed through the VPN. The Kubernetes cluster basically plays double duty. In addition to hosting the MLP and DICOM adapters, we're also hosting services. So the classic service-oriented architecture, microservices, pulling together a specific set of business logic to accommodate a particular business task into a specific process. And these processes do various things. For example, in this use case, we're creating orders. So as messages come into the system, they emit notifications into Cloud Pub Sub. We'll talk more about that in particular. And these services listen for those notifications. And when they get those notifications, they do specific things. So for example, they might listen for a DICOM message and then create the associated ORM HL7 message. They might listen for the ORM HL7 message, and then create an order in the transactional Cloud SQL database in the iDigital application itself. Resource matching, Omer was mentioning that briefly. How do you match an HL7 message to its DICOM study? How do you do all these things? So, and then finally, billing. We highlight billing as well, of course, major component of the system. You want to think about how those bills then need to be delivered to those organizations. Healthcare API, all kinds of interesting things happening here that Patrick will talk about in specific detail, but some of the things that I wanted to highlight in particular for this use case and implementation are the data store architecture design. So we have highlighted here in the application, in the architecture, 3 different data stores, one for ORMs and ORUs, so that's requests for reports, and then the report reply, DFTs, detailed financial transaction ORM, detailed financial transaction HL7 messages, and then of course DICOM messages. So ORM and ORU are in one data store, DFTs are in another data store, DICOMs are in their own data store, and we had an interesting design decision to determine, well, do we need one for real time and do we need one for priors? Or for those not in the business, the archive of all of the previous images that were done. And due to how different microservices, we've architected various microservices in the system, we decided to put them all together in one DICOM store. Each of those data stores then output into their own Cloud Pub Sub topic, and these topics, of course, are critical. This is where the microservices listen for various pieces of information, put in new pieces of information, and there are many ways to interact with these Pub Sub stores. The takeaway for these is that it's completely integrated. So this is completely managed by Google Cloud Platform. There's all kinds of capabilities to interact with the queues, to act or acknowledge messages from the queue, or not acknowledge messages from the queue, ensuring that they get picked up at a later date, configurable retention, the messages stay around until they're processed, et cetera, et cetera. BigQuery. This is a really interesting part of the conversation, and I spoke a little bit about it at the intro. Omer mentioned it. Going to the cloud shouldn't be an apples to apples conversation. It should be an apples to fruit basket conversation. You get all the things, because going to the cloud unlocks all of the other opportunities in the cloud. In particular here, we're highlighting BigQuery. So BigQuery is Google's data warehouse system. And once you get data into BigQuery, you can do all kinds of interesting things. You can enable analytics. You can enable more advanced analytics we love to call machine learning. Sprinkle a little bit of machine learning on everything and everything's better, right? But you gotta get the data there first. It has to get there. The way that we've designed the healthcare API is that it easily can export data into BigQuery. And cannot underestimate easy. Easy is incredibly important. BigQuery's got all the goodies. It's scalable, it's fully managed, auditable again, integrates with external reporting tools like Looker and Our Data Studio, Tableau, accessible via standard ANSI SQL. So for those of you in the audience who have a SQL background, this is fantastic. eUnity Viewer. The eUnity Viewer is the DICOM viewer itself. So this is a commercially available product from another company. We integrated, it integrates directly with the healthcare API. It's specifically designed to have various pieces of functionality segmented. So we have a front-end web application. We have a data cache proxy. We also have a computational engine that just executes 3D volumetrics. And the key takeaway here is that because it's delineated, you can execute specific fine-grained access controls. The iDigital application itself runs in its own project, and it has many different components running in virtual machines, using Cloud SQL, storing all its data in the transactional database, has its own access control for front-end users, and ultimately, again, is separated from the services that access various parts of the system. So this is security isolation and reducing that footprint that might cause challenges from a security perspective. Talked a lot about the logging, separate project for logging, specifically an opportunity to segment all logs and make them only available to your compliance organization. Again, HIPAA best practice, isolation, ability to transfer these logs into BigQuery, similar to the clinical data, do all kinds of advanced analytics, anomaly detections, do we have problems, are the wrong people accessing this data, et cetera, et cetera. Finally, because this system is so flexible, you have the opportunity to send your data to various billing providers. And the billing providers, of course, like everybody else, don't really share standards. So you need to be able to speak to the specific billing provider that your customer has a contract with, and what are their capabilities. Native APIs, being able to send specific billing DFTs, the batching, CSVs. This again ties into the service, microservice architecture, being able to create the right materialization of your billing log and get that sent to the billing provider in the way that they can consume it. And again, it's the system here is delineated within its own microservice architecture. So with that, just a quick recap. This was a really very fast walkthrough of a complete end-to-end architecture with zero on-prem footprint. Completely in the cloud. Everything is operating in the cloud using many different GCP pieces of functionality. Everything is automated. Everything I talked about here can be automated, and we're working continuously to do that, to create the automation scripts with iDigital, Cloud Deployment Manager, G-Cloud, Kube Control. Finally, we leverage many different components of the cloud. So it's not just healthcare API. You got to bring all the other pieces together. Networking, security, BigQuery, and ultimately the healthcare API itself is storing this very critical healthcare data. And with that, I want to pass the baton to my colleague Patrick, who will tell us more about the healthcare API.
Thank you, Sasha. Thank you, Sasha. So what is the healthcare API? We've heard a lot about it in Sasha's architecture. So fundamentally, the way we think of it is it's a managed, scalable, and secure platform for your healthcare data. So we built the healthcare API to be interoperable. So that means it can talk to your existing systems in the healthcare space. And it also supports industry standards that we encounter in the healthcare space. We've designed it to be developer-friendly and easy to use for our customers. Of course, security and compliance are very important concerns in the healthcare area. So we built the healthcare API with robust security and compliance features in mind. Finally, the healthcare API is designed to allow customers to really unlock the value of the data that they store in it. For example, this is done by integrating with powerful analytics and machine learning solutions. So as we heard earlier in the talk, most customers in the healthcare space today have data stored in a variety of different on-prem systems. Typically, those are fairly fragmented or siloed, so you'll have separate data systems for different types of data, different systems maybe for different geographical locations. You might have different systems in different parts of a healthcare organization. And it's very difficult for data to kind of like travel from one of those systems to another. So what we've done with the healthcare API is we are aiming to allow our customers to bring all their data together in a single place. The way we've done that is by integrating with existing systems. So this includes PACS and VNA systems. So those are systems that customers use to manage their imaging data today. And also integrating with EHR systems, which have structured healthcare records. We heard a little bit about this earlier. We support natively a number of kind of the most common formats that we encounter in the healthcare area. So on the imaging side, this is primarily DICOM. So DICOM is a format for storing medical images and also the metadata pertaining to those images. On the electronic health record side, we support FHIR and HL7. We heard a little bit about the adapters also. So these are some open source components that we've put out there to make it easier to interact with what we think of as the legacy protocols of exchanging those types of data, notably DICOM DIMSI as well as MLLP. So what do we mean when we say the healthcare API is developer-friendly? Well, like most GCP APIs, it's a modern RESTful API built on top of HTTPS and gRPC. So the goal for us really was to allow customers and developers to focus on their business logic while Google would worry about things like backups, configuring VMs, and setting up databases. The healthcare API is a fully serverless API, so that means all scaling and serving infrastructure is all handled by Google's infrastructure. We integrated the healthcare API with Google Cloud Console, so this provides our customers with a graphical user interface for easily managing the resources stored in the API. Cloud PubSub, I think we heard about it in Sasha's diagrams. This is just a very powerful, versatile mechanism for plugging in any kind of like custom processing logic into your healthcare workflow. So we think of it as almost the Swiss Army knife of integrating with our API. Healthcare data is probably one of the most sensitive types of data out there, and I'm sure most of you will know that privacy is heavily regulated in the healthcare space. So that's why we designed the healthcare API from the ground up with a very robust set of security and compliance features built right in. Like all of Google Cloud, the healthcare API is built on top of Google's trusted infrastructure, so it benefits from the same multi-layered security. We have built-in fine-grained access control. So this allows customers to use Cloud IAM and specify exactly who gets access to what parts of their data. And then they can also go to Cloud Audit Logging, where they can verify who's actually looking at what and maybe detect any anomalies that might have occurred. HIPAA compliance is table stakes when handling healthcare data with personal information in it. So we built the healthcare API to support HIPAA compliance, and we regularly sign BAA agreements with our customers in this space, which is a legal requirement. We have also built the healthcare API to support data locality. So what this means is a customer can specify where in the world they want their data to be stored. This is important for healthcare customers in many jurisdictions where there are data residency requirements that they have to comply with. One of the key benefits of using the Cloud Healthcare API is that it allows customers to bring all their healthcare data from where it resides today and assemble it in a single place where they can reason about it holistically. And finally, we also have some mechanisms in the Cloud Healthcare API that allows customers to then take those models and actually deploy them into a clinical workflow. So for the remainder of the talk, I'd like to walk you through three key scenarios or three key use cases that we've encountered when working in this space. So first of all, I'd like to describe how we can support research and clinical viewing of medical images using the Cloud Healthcare API. Next, I'll talk a little bit about high-performance analytics using BigQuery. And finally, I'll get into machine learning and how to train and deploy models there. So the Healthcare API is a flexible platform for viewing medical imaging data. Images can be ingested into the Healthcare API either from a PACS system directly, so this is kind of similar to what we saw in some of the architecture diagrams previously, so where we have images traveling from an on-prem PACS system into the Healthcare API, maybe using one of our adapters. But we also support bulk import from Google Cloud Storage. And the nice thing about the bulk import piece is that it actually enables customers to use things like the transfer appliance. So this is a tool that allows customers to do bulk loads of very large amounts of data that would maybe take a very long time to send over the network. With the transfer appliance, we can bypass that and get it into the Healthcare API more quickly. We have then worked with a number of partners to build Healthcare API support into medical imaging viewers. So we already heard about one of them, Unity. There's another commercial viewer, IMS, that's also supporting the Cloud Healthcare API. But we've also worked with a number of open source projects. So WeAssist and OHIF are a couple of open source viewers that also can talk to the Healthcare API directly. So for all of these, they can fetch the images directly from the API, so it's a truly serverless end-to-end viewing experience. On the analytics side of the story, we rely heavily on BigQuery. So BigQuery is Google's petabyte scale, high performance analytics engine. It's something we built originally for our own internal use at Google to understand user behavior on some of our consumer-facing products. So via the Cloud Healthcare API, we're making this powerful tool available to our customers in the healthcare space by allowing customers to load their healthcare data into BigQuery. Once their data is in BigQuery, it becomes very easy to join across different data modalities, join in additional data sets, maybe join in some public data sets. We have some of those available, like the RxNorm data set, which is a prescription drug database. So you can maybe combine your healthcare records data, your imaging metadata, and maybe some genomics data, and then you can sort of really start to reason about those. So there is a nearly endless list of use cases for this. So I'm kind of highlighting 3 of them here. So we've got some customers that are using BigQuery to identify and select cohorts to include in research studies. So select a list of patients, for instance, and then maybe materialize their data, de-identify it, and hand it over to researchers. We've also seen customers using BigQuery for clinical decision support. So this is an example where maybe we want to find similar patients to the one that a provider is currently looking at. And finally, because BigQuery is fast, it allows fast turnaround on queries. So it's a very useful tool for iterating on things like quality and performance metrics, where we want to start measuring things in the healthcare enterprise that are very hard to do in the existing on-prem silos. Finally, let's talk a little bit about machine learning. So one of the key benefits of the Cloud Healthcare API is that it can bring your healthcare data to advanced machine learning solutions. So these machine learning solutions, again, can take advantage of the full spectrum of healthcare data. It can, healthcare records, imaging data, genomics data, you name it. We integrate with some powerful labeling tools. So those can be used by customers to curate high-quality training data sets for their machine learning use cases. And then we can make those data and labels available to Cloud Machine Learning Engine and AutoML, which are some of the advanced machine learning tools built into Google Cloud Platform. So Cloud Machine Learning Engine, you can think of it as our hosted version of TensorFlow. So this is something that allows serverless training of machine learning models. AutoML is a tool that's sort of specialized for customers that may not have a lot of data science or machine learning expertise at their disposal. And it's a powerful tool that can allow customers to train models even in those contexts. Finally, once a customer has trained a model, the Healthcare API can also help them deploy this model back into their workflow. So for example, if I have a model that can help me understand an X-ray image, I can use the Cloud Healthcare API to bring the prediction from that model back into the existing PACS sphere so a radiologist can view the model prediction alongside the images when they're doing their read. One thing I would like to announce is that the Cloud Healthcare API, as of last week, is actually available in public beta. So that this means it's something that's now available to all Google Cloud customers to use. We also have some public data sets, some public imaging data sets available, hosted on the Cloud Healthcare API already. So this can be a great place for you to start playing with some of our viewer integrations and maybe start trying out some of the tools that we discussed today. So notably, we have the NIH chest X-ray data set on there, and we also have the cancer imaging archive on there. All right, so with that, I'd like to thank you all for your attention.